Hello everyone. Today we're talking about 13P Atlas again, but this time with fresh and fascinating scientific data. You might be thinking, wait a minute, the comet is still hidden behind the sun. How do we have updates? The answer lies in observations made a few weeks ago, when the powerful Keck telescope captured revealing spectroscopic data. Let us find out what 13P Atlas is ejecting and what it tells us about the comet's true nature. Before diving into the discoveries, we need to understand the tool that made this research possible. The W.M. Keck Observatory, located atop the dormant Mauna Kea volcano in Hawaii, houses two of the most powerful optical telescopes in the world. At an altitude of 4,145 meters above sea level, the observatory sits above roughly 40% of Earth's atmosphere, providing exceptional observing conditions. Each of the twin Keck telescopes features a 10-meter segmented primary mirror, a marvel of modern engineering. But what truly matters for this story isn't the size of the mirror. It's the world-class spectroscopic instrumentation these telescopes carry. Spectroscopy is one of the most powerful tools in modern astronomy. Rather than simply capturing an image of a celestial object, a spectrograph disperses the light into its component wavelengths, essentially creating an extremely detailed rainbow. Every chemical element and molecule leaves a unique signature in this spectrum. Dark absorption lines or bright emission lines at specific wavelengths. These spectral signatures are like chemical fingerprints. When we see an emission line at a particular wavelength, we can unambiguously identify which element or molecule is producing that light. This technique allows us to determine the chemical composition of objects billions of light years away, a capability that almost feels magical when you stop and think about it. It's mid-October 2025, and 13P Atlas is currently transiting behind the sun from our Earth-based perspective. The intense solar glare makes direct observation impossible at this moment. We will have to wait roughly 2 more weeks for it to emerge from the other side of the sun, when extensive new observations will finally be possible. But science rarely waits idly. The observations we are discussing today were conducted on August 24, 2025, when 13P Atlas was about 2 astronomical units from Earth. An astronomical unit, abbreviated as AU, is the average distance between the Earth and the Sun, roughly 150 million kilometers. Therefore, the object was approximately 300 million kilometers away during these observations. At that time, the comet was still sufficiently separated from the Sun in the sky to allow for detailed telescopic observations. The Keck team seized this window of opportunity, aiming their powerful spectrographs at the interstellar object to collect data on its chemical composition. The results of the spectroscopic analysis were recently published and reveal fascinating details about the composition of 13P Atlas. 2 detections stand out as particularly significant: cyanide and gaseous nickel. Cyanide, chemically represented as Cn, is a molecular radical consisting of a carbon atom triple bonded to a nitrogen atom. In comets, cyanide does not exist in this form in the frozen nucleus. Instead, it is a product of photodissociation, the process by which larger, more complex molecules are broken apart by intense solar ultraviolet radiation. Sunlight does more than just heat comets. It bathes them in high-energy radiation capable of breaking chemical bonds. Complex organic molecules embedded in cometary ice, when exposed to solar radiation, fragment into smaller, simpler radicals. The cyanide observed in the coma of 13P Atlas likely originates from the photodissociation of more complex carbon and nitrogen-containing precursor molecules. The second discovery, gaseous nickel, is even more intriguing. Metals in gaseous form are relatively rare in comets, though modern observations are revealing them more frequently. Nickel, along with iron, is one of the most abundant metals in the universe, a major component of rocky planet cores and metallic asteroids. Its detection in the coma of 13P Atlas hints at either unusually high metal content in the nucleus or processes that liberate metals into the gas phase more efficiently than previously understood. One of the most revealing aspects of the spectroscopic analysis was not just what was being emitted, but where it was coming from. The spectra showed that the emissions were clearly concentrated in the anti-solar direction, that is, on the side of the comet opposite the Sun. This configuration makes perfect physical sense and aligns exactly with what we expect from a normally behaving comet. The side of the comet's nucleus facing the Sun receives intense radiation, heating the surface ices and causing sublimation. The resulting gases primarily escape from this sunlit side, forming directed jets that then flow away from the Sun under the influence of radiation pressure and the solar wind. The spatial distribution revealed by the Keck data shows Cyanide, Cn, being detected approximately 840 kilometers from the comet's central nucleus. This substantial distance indicates that Cn is not only being produced at the immediate surface, but is propagating through the coma as photodissociation processes continue converting precursor molecules into cyanide. Gaseous nickel, on the other hand, was detected at roughly 200 kilometers from the nucleus. This more compact distribution suggests that nickel is being sublimated directly from metallic grains on or near the surface, without undergoing the same cascading photochemical processing that produces cyanide farther out in the coma. In short, the spatial patterns of Cn and nickel provide a dynamic snapshot of how different materials are released and processed in the comet, offering crucial clues about both its composition and the physical mechanisms at work. ChatGPT dice, at the time of these observations, 13P's atlas was 2.75 astronomical units, AU, from the Sun, more than 2.5 times the Earth-Sun distance. At this distance, the intensity of sunlight is reduced to less than 15% of what we experience on Earth. Yet, it was still sufficient to heat the cometary nucleus and trigger sublimation and photodissociation processes. This distance detail is crucial for correctly interpreting the observations. Different volatiles sublimate at different temperatures and therefore at different distances from the Sun. Water ice, for example, begins to sublimate significantly around 3 AU, while carbon dioxide ice sublimates at much greater distances, even beyond Jupiter's orbit. The activity observed at 2.75 AU confirms that 13P Atlas contains volatiles abundant enough to produce detectable emissions even at this relatively large distance. As the comet continued its approach toward the Sun in the following weeks, this activity would have increased dramatically, producing more intense gas and dust emissions visible to telescopes. An intriguing aspect of the Keck observations was what was not detected: gaseous iron. Many solar system comets that show nickel emissions also exhibit iron emissions, which is typically even more abundant than nickel in cosmic materials. The interstellar comet 2I Borisov displayed both nickel and iron. The apparent absence of iron in 13P Atlas's spectrum might initially seem anomalous. Some could argue that this suggests fundamentally different behavior compared to known comets, perhaps implying the object is unusual or even different in nature. However, the correct interpretation is more nuanced and instructive. Recent research indicates that iron emission in comets can be strongly heliocentric distance dependent. That is, it varies with the comet's distance from the Sun. Different sublimation and excitation mechanisms operate at different distances. It is entirely possible that 13P Atlas will begin to exhibit detectable iron emissions either closer to the Sun or, in some cases, even at greater distances, depending on local conditions. This distance-dependent behavior reflects the complex physics of cometary processes. Sublimation isn't simply an on-off switch. Different metallic compounds have varying vapor pressures, sublimation points, and mechanisms for release from the surrounding ice matrix. The exact temperature, ice composition, and porous structure of the material all influence which species are detectable and when. One of the most fascinating aspects of this research is the emerging comparison between interstellar objects. We now have data on 3 confirmed visitors from beyond our solar system: 1I Oumuamua, 2I Borisov, and 13P Atlas. Oumuamua remains enigmatic due to the brevity of our observational window. Discovered only as it was already leaving the inner solar system, it displayed no detectable cometary activity, fueling intense speculation about its nature, perhaps an interstellar asteroid, or possibly a fully degassed comet. 2I Borisov was clearly cometary, with a well-developed coma and tail. Spectroscopic analyses revealed both cyanide, Cn, and gaseous nickel, just like 13P Atlas does now. This similarity is extremely significant. It suggests that, despite originating from completely different stellar systems, potentially separated by hundreds of light years, these objects share fundamentally similar chemical compositions. What does this tell us? That planetary formation processes, protoplanetary disk chemistry, and the condensation of ices and minerals must be remarkably universal. The same basic physics and chemistry that operated in the protoplanetary disk forming our solar system 4.6 billion years ago also operated in disks around other young stars elsewhere in the galaxy. Here we reach a crucial point that contextualizes the entire discussion about 13P Atlas and the anomalous behavior some observers perceive. Currently, we have only 3 confirmed interstellar objects to study. 3. That is a statistically insignificant sample. Imagine trying to understand the diversity of life on Earth by examining just 3 organisms. You might happen to pick a bacterium, a giant sequoia, and a blue whale. These 3 share fundamental DNA-based biochemistry, yet they are radically different in almost every other way. It would be absurd to try to infer general rules about typical terrestrial life from such a tiny sample. The situation with interstellar objects is analogous. Our solar system contains billions of comets, asteroids, and minor bodies, exhibiting enormous diversity in composition, structure, orbit, and behavior. If the interstellar population is similarly diverse, and there is no reason to believe it wouldn't be, then 3 objects are simply not enough to establish norms or identify genuine anomalies. This is where the Vera C. Rubin Observatory enters the story. Scheduled to begin full scientific operations soon, the Rubin Observatory will carry out the Legacy Survey of Space. This revolutionary survey will uncover transient phenomena of all kinds, supernovae, asteroids, comets, and crucially, interstellar objects. Projections estimate that the Rubin Observatory could detect dozens or even hundreds of interstellar visitors over its decade of operations. When we finally have data on 50, 100, or 200 interstellar objects, we will be able to make statistically significant statements about their typical properties and identify genuine outliers. Until then, each new interstellar visitor is simply another data point in a parameter space that is still extremely sparsely sampled. Focusing on 13P by Atlas specifically, every new observation, including the recent Keck spectroscopic data, confirms that the object is behaving entirely like an active comet. The cyanide emissions are normal for comets, and the detection of nickel, while less common, has also been observed in other comets. The anti-solar distribution of these emissions is exactly what physics predicts, and the apparent absence of iron, initially intriguing, likely reflects heliocentric distance effects that are still being studied. There is nothing in the Keck data that requires or even suggests exotic explanations. Each observation simply reinforces the cumulative picture. 13P Atlas is an interstellar comet behaving precisely as comets are expected to behave. The story of 13P Atlas is far from over. Several space missions will have the opportunity to observe it as it travels through the solar system. The Juno spacecraft orbiting Jupiter, the Europa Clipper mission en route to the Jovian system, and potentially other spacecraft may capture additional images and data. There is also the matter of observations from Mars orbit. Multiple orbiters around the Red Planet, including Chinese, European, and American missions, had the chance to observe 13P Atlas during its close approach. Some of these images have already been released by European missions, such as Mars Express and the Trace Gas Orbiter. NASA has not yet released data from its Martian orbiters, likely due to internal operational procedures, but these datasets are expected to become publicly available in time. Each new observation from every telescope and space mission adds pieces to the puzzle. Spectroscopy across different wavelengths, photometry in multiple bands, and observations from varying geometries all contribute to building a complete understanding of this fascinating visitor. The study of 13P Atlas exemplifies modern planetary science at its finest. Careful observations using world-class instrumentation, rigorous analysis of spectroscopic data, comparison with other known objects, and contextualization within our theoretical understanding of cometary physics. This is science operating exactly as it should. The detections of cyanide and gaseous nickel are not sensational in a tabloid sense, but they are profoundly significant scientifically. They tell us that this visitor from another stellar system shares fundamental chemistry with objects formed within our own solar system, reinforcing our understanding of the universality of astrophysical processes. 13P Atlas remains exactly what it has always been, a fascinating scientific object, a natural laboratory for studying conditions in other planetary systems, and a rare opportunity to examine material formed around another star. It doesn't need to be an alien spacecraft to be absolutely extraordinary.